Okay, so maybe first I will introduce myself. Most of you know me, but still, Noemi Zabari. I was actually finishing my PhD here at this institute. And that's how I get to know Credo and the idea of Astrotech AI. Formerly, it was called Astrotectonic, but then some people said that it's too difficult to pronounce when they do not hear the word and they need to read that. Hence, we changed it to Astrotech AI. And the project is quite big, but I will talk about what we are doing in the machine learning topic and where are we at right now. I'm presenting, but I didn't do that. Who did it? It's Kamil Zieliński, who is our machine learning specialist. He's living in Poznań, but I think now he's somewhere else. So the goals are to use machine learning tools to predict whether an earthquake will occur or not. And we have a defined framework. We have defined distance from the cosmic ray stations. And those stations that we are using for these results are 3 stations. But let's start with the databases. We are using data from the World Data Center for Cosmic Rays. And we have 3 stations listed here. And the earthquakes are from USGS database, which are also available online. That's the stations. That's how they look on the map. So you can see the locations more or less. So the model input consists of the past 360 hours. So it's approximately 15 days. We are looking at the 15 days before the earthquake event. And we have those 3 stations, and along with the information about the time elapsed since the last earthquake. And model output is that we are looking for the earthquakes of magnitude with the magnitude greater than 6, and within the next 14 days, and the distance that we are looking at. So we want to localize this problem is 1,000 kilometers from those 3 stations. So sorry for the graph. It's like just to show that's the time we are looking at before the event station. So we have 3 stations, 15 days before, 24 hours and 1 cosmic ray measurement, which gives us 1,080 numbers. And we build autoencoder so to attempt to condense those 1,080 numbers into 20 features, and then accurately reconstruct original cosmic ray rate sequences. And next step is that we have, for that modules, we have neural net based autoencoder, and we have also a LGBM classifiers, which is trained using output of autoencoder and is combined with additional feature, which is time since last earthquake feature. It's over there in the upper corner. And then we come up to the 1 classifier. So the classifier estimates the probability of an earthquake for magnitude 6, 14 days before, within 1,000 kilometer distance of any station. And this estimation is based on compressed cosmic rays data and the time elapsed since the last earthquakes. So we come up to the 1 number, which gives us estimated probability. We are splitting the data. So time-aware data is split into training, validation, and test, 50, 25, and 25%. That's the proportions. And we are using metric for evaluation and statistical significance, which is average precision. And the performance of the model, we have models test IP, the numbers that you can see, both models test and the baseline. So for the optimization and the statistical significance testing, it's good, but it doesn't provide much insight into actual model performance in our context. We have, the average precision evaluates every individual precision, but we don't have the answers that we care about, like how many earthquakes can we detect in advance and what is the false alarm ratio at specific detected earthquakes level. And that's why we created earthquake-focused performance metric with these following assumptions. We count false positive and true positives over 14 days period. A false positive is recorded if any false positive alert occurred within the 14 days period. And a true positive is recorded if any alarm occurred within the 14 days preceding an earthquake. And that's the earthquake detection trade-off curve. The baseline false alarm rate is the average false alarm rate expected from the random model. I also have a note here to say that this calculation can be done determining the false alarm rate in scenario where an alarm is analyzed always raised, meaning that the probability threshold is equal to 0. Okay, and that a random model's performance won't improve even if we increase the threshold, because its probability of being incorrect remains constant. About statistical significance test, we have 300,000 experiments that we made, and each with different seed. The predictions were distributed randomly from within the 0 and 1, and none of these experiments could exceed the average precision performance of the model, which is a strong significance for sigma 6 or even more. And the conclusions, which are the most important part, is that machine learning, it appears to confirm the existence of the cosmoseismic correlation. And even if the metrics are not really impressive, it could translate into significant real world effects. It seems that we can forecast at least a few % of massive earthquakes with a decent false alarm rate, which is below 30%. And of course, it is very important to notice that we do not have predictions of earthquakes till now. So this is a very good, at least, starting point for that. Just the quick overview of the company, because we are a company. Besides that, besides working on Cosmic Ray channel, we are going for multi-channel approach, which means we want to implement many different observational channels into one system, looking at them so that we can cross-correlate data and cross-analyze data. We are doing right now the first two, which is Cosmic Ray, of course. And we are using satellite data with the help of very strong organizations. Those are SAR, which is synthetic apparatus radar, and LST, which is land surface temperature. We are looking at the anomalies, we are looking at the changes of temperature, and SAR, we are looking at the small ground deformation that are happening before earthquakes. That's the organizations that I mentioned. We are doing it with ESA, with European Space Agency, Polish Space Agency. We are doing that with Deutsche Telekom, who are helping us on the detector side, with on the telecommunication part. And we have also Israel Aerospace Industries, of course, NCBJ, who we know, Credo, as in the middle of the slide, but also Institute of Geophysics of Polish Academy of Sciences, who has the seismological lab here in Krakow, and we are cooperating with them, and other parties. That's it. Thank you so much.
Thank you very much. Really impressive questions, Robert.
Noemi, let's imagine that Marcin succeed in this collaboration with Mexico colleagues concerning net of some devices, some detectors in Mexico. How can you, the first question, whether you see your role, I mean, also tectonic role played in this project, and if you see your role, what it can be?
Definitely, we see, of course. I hope it will work. We can help on many at many places, because we have a strong software team, and we have strong team that is specializing also in analysis using machine learning. So that's how we are. I think I see us, help, support, and contributing.
And probably small question. Do you know any other company in the world which can compete with you at this level?
Yes, definitely. It's apparently we do have competitions. It's good because we are challenged many times with, you know, this thinking that earthquakes are unpredictable. That's why it's good that we have competition. There is a company, AETA, in a Chinese company. They are already operational for 10 years or 6 years, okay? 1 year, they are working quite, the last 1 year, they are working quite nice. They can predict earthquakes a week before without specializing which day. They can say that in this week, there will be earthquake without specifying the time, exact time of it. And their equipment, the technology is based on acoustic. They are using, what do they use? They are using some acoustic technology, which infrastructure that they need to build is very, very expensive. There are also other. There is a Seismic AI. There is a Terra Seismic, Israeli company. The Terra Seismic is from US. With cosmic radiation in specific. There is a company called Precursor, but they are looking at ionospheric disturbances.
Yeah, so generally speaking, what we see is that there is kind of a wave of companies or people that try to forecast earthquakes, which is amazing because all of the geologists or most of the geologists that we spoke with, they conceive earthquakes as unforeseeable. And today you saw that it is possible. Yeah, but our main advantage is the cost versus time in advance. So using 10 detectors, we can forecast, at least according to this model, 10% of all major earthquakes with about 80 to 90% certainty. So that's 1,000 square kilometers where AETA can forecast during that week, but they require 3 detectors for 100 square kilometers. And the differentiation in the price is huge. They require that their detectors cost in hundreds of thousands of dollars, and our 10 detectors cost between $40,000 to $50,000. So in magnitudes better, in magnitudes lower.
But also the uniqueness is the cosmic channel, right?
Yes,
that's really the really unique approach in the world to answer Robert.
And it's actually a crucial, I would say it's a very crucial point and a novel approach. So it's something worth to do. Of course, what we see, the more data, the better results of the algorithm, as algorithm has more data to learn on. So it's worth to work on those detectors around the world and create the network of data.
A very short question.
I missed one point at the very beginning of your talk. These 3 sites you showed, Tbilisi and 2 else, they are sites of what? These are cosmic ray observatories or what? Because
the data that we are
it's concentrated.
Yes.
And you base on it.
Yes.
Yeah, it was. I think
and one I think important point. So, yeah.
Data is taken from this. It's open source data.
Yeah, and just so you understand the quality of the data, though, so that's a couple of tens of megabytes of data. And our detectors in 1 month, the Pro detector will collect about 43 gigabytes of data. And so we expect this model to perform extremely well with the data collected with our detectors.
Simon?
I have a very short question. Maybe if you have these historic records from these 3 sites and you build your model based on them, have you tried basically detecting the earthquakes in one site with the model you trained on the data of another? So how is the model so robust that if you set up new cosmic detectors at a new site, that you can then instantly start prediction for the site?
Not instantly, because the format of the data is for each data is a bit different. This takes time. We need to build a new, okay, take it.
So initially, Noemi's answer was accurate. Initially, no, but just recently we've upgraded our system to be able to work with multiple site. So it's very easy for us to add cosmic ray detection site. And this model has also been tested on data that was collected in Japan. So we took 3 stations in Japan, and this model worked there as well.
Okay, maybe one last comment, not a question, so you don't need to answer, but if machine learning approach really confirms the existence of the cosmoseismic effect, that would be an excellent topic for an article. If you might consider this, that would be an excellent news. Let's thank Noemi again.